Would an alien looking at Earth from light years away be able to detect the vibrant life that covers the planet? Perhaps not. Even from the moon, the Earth looks like a swirling blue and white marble, with perhaps just a hint of green. And from just outside the solar system, our planet is reduced to a single pixel, a pale blue dot in the dark expanse of the cosmos. But with the right technology, aliens might just be able to detect the changes that life has wrought on our planet during its 3 billion or so year tenure. It's these very changes that astrobiologists on Earth are looking for as they search for extraterrestrial life. And we're finally on the brink of discovery, using 200-year-old technology in the most advanced telescope we've ever sent to space. In the early years of the 19th century, a multi-talented scientist, William Hyde Wollaston, was living alone in London, experimenting with sunlight. He used a lens and a prism to focus the light of the sun onto a screen, breaking its whitish glow into a rainbow of colours. The idea of a spectrum wasn't new. It had been discovered and named by Isaac Newton some 130 years earlier, but Wollaston's higher resolution setup showed something new and puzzling. There were gaps in the spectrum, dark lines that broke up the smooth gradation of colours. Wollaston had no explanation for these gaps and argued that they could be the natural boundaries between true colours. In fact, it would take another decade or so and a different optical scientist to figure out the truth. Joseph von Fraunhofer was a Bavarian physicist with the Benedictine monks on his side. In a secularised monastery specialising in glassmaking, Fraunhofer made some of the most precise optical instruments of the time. That allowed him to not only recreate Wollaston's experiment, but also refine his observations of the spectra and the dark lines that interrupted them. And so, he created the first spectrometer. This is a very substandard modern recreation of a spectrometer that uses a shard of a DVD rather than a prism to break up the light. The thin beam of light that passes through the slit is split up into its spectrum, which is then imaged by the webcam and analysed by computer software. Different light sources produce different spectra. And when you put something between a light source and the receiver, then some of the light gets blocked. Like here with this green food colouring, the spectrum shows a drop in the red because it's letting the green and some of the blue light through. This is what Fraunhofer saw with the very first spectrometer, and it allowed him to figure out what he and Wollaston had been seeing in the sun spectrum. If certain compounds can stop specific wavelengths from getting through, then gaps in the spectrum must be caused by absorption by specific elements. The lines in the sun spectrum correspond to the elements and molecules that make up the outer layers of the sun, that absorb the light coming from the inner layers as it makes its way out. The dark lines became known as Fraunhofer lines, and the science of spectrometry was born. But how will that help us find aliens? We've known for about 30 years that there are other solar systems out there. Planets orbiting their star, like the Earth and its companions, orbit our sun. And as of 2021, we've detected more than 4,000 of these so-called exoplanets, with more than 2,500 still waiting to be confirmed. Since planets are so small and so dark compared to their stars, scientists need to use special tricks to identify them. One of those tricks is planetary transits. When a planet passes in front of its star, it blocks a tiny fraction of the star's light from reaching our eyes and our instruments. A sensitive enough instrument can detect that dip in light, and if that dip keeps happening on a regular basis, there's a pretty good chance that it's caused by an orbiting planet. Based on how big the dip is and how often they see the dip, scientists can work out how big the planet is and how close it is to its star. But enterprising astronomers can go one further. The vast majority of a transiting planet is opaque to the star's light, but its atmosphere isn't. A tiny fraction of the star's light will pass through the thin shred of atmosphere around the planet's circumference. And just as Fraunhofer looked at the spectrum of the sun, scientists can look at the spectrum of this sliver of light to work out what exoplanet atmospheres are made of. Only it's hard to grasp just how little light there is to work with. Instead of something like this, it's definitely something more like this. For an Earth-sized planet, just 1/10,000,000th of a star's light will pass through the planet's atmosphere. So the instruments that measure that light need to be incredibly precise and calibrated to within an inch of their lives. But this isn't some pipe dream. Dozens of exoplanet atmospheres have already been analysed using telescopes and instruments on Earth and in space. The first was from a giant hot Jupiter-like planet 160 light-years away, named HD 209458b, but nicknamed Osiris. Being hot meant that its atmosphere was extended, so astronomers had more to work with. And in 2001, a team reported that they'd spotted a dip in its atmospheric spectrum that corresponded to the element sodium. For the first time ever, we knew what made up the air of an alien planet. But Osiris is no Eden for alien life. Its surface is more than 1,000 degrees, and so water and organic molecules don't stand a chance. To find smaller, cooler, Earth-like atmospheres, we need to go one better. Enter the James Webb Space Telescope. This ambitious new telescope is being heralded as the next generation of space-based astronomy, and it's the most complex instrument we've ever sent into space. Only, it's not in space yet. Webb is so cutting edge and uses so many new and untested technologies that it's been beset by years of delays. But it's getting there, and NASA hopes to launch it later in 2021. When you look at it, it's not hard to understand why it's taken an age to get right. It's dominated by a huge sun shield made of 5 thin membranes, each the size of a tennis court. This sun shield will block the heat from the sun, keeping the scientific instruments icy cold for the best possible precision. That's especially important since Webb won't be looking at the universe in visible light, but rather the infrared. We can't see infrared light, but experience it as heat. So this huge and complex telescope will be sent 1.5 million kilometres away from Earth to turn its back on the Sun and scan distant stars for signs of exoplanets. As a successor to the Hubble and Spitzer space telescopes, Webb will use its 6.5-metre gold-plated mirror to collect as much infrared light as possible. So it's ideal for analysing the thin atmospheres of rocky exoplanets. Infrared spectra show even more absorption lines for different chemicals than visible spectra do, something Fraunhofer couldn't have known, since the Earth's atmosphere does a really good job of absorbing almost all the infrared radiation from the Sun. So the Webb telescope, when it finally gets up and running, will give us the best chance yet of scanning the atmospheres of planets trillions of kilometres away, using a technique devised 200 years ago. But could this really help us find alien life? Pictures we've taken of Earth from space show that even the biggest superstructure soon disappears with distance. So astrobiologists need to use other proxies for life if they hope to detect it from light years away. And conveniently, one of those proxies happens to be in a planet's atmosphere. Gassy atmospheres can come to swaddle a planet in several ways. They can be captured from free-floating gas around a star, they can be delivered by bombarding asteroids or comets, or they can be outgassed from the interior by volcanic activity. The composition of an atmosphere depends on how that atmosphere was created, but also on any processes going on the surface to modify it. And on Earth at least, life has done a pretty thorough job of modifying the atmosphere. Photosynthesis, which uses the sun's light to transform carbon dioxide and water into sugars for life, also belches out a waste product, oxygen. When photosynthesis first evolved billions of years ago, that oxygen started building up in the oceans and atmosphere. And today, oxygen leaves its mark on our planet's atmospheric spectrum. An alien looking at Earth with a Webb-like spectrometer would be able to see that our air is rich in oxygen. Combined with more threads of evidence, like the other gases in our atmosphere and the temperature of the surface, they could reasonably conclude that this small rocky planet, third from its star, does indeed host life. While life certainly can and did scrape by without photosynthesis, it's plants' ability to eat the sun that really set us free. Life could colonise everywhere the light touched, and it had an inexhaustible supply of energy with which to build elaborate biological structures and complex ecosystems. So oxygen, detected as a dark stripe in a faint rainbow in an unimaginably small sliver of light, could be the first clue to finding biological success elsewhere in the cosmos. And as soon as the James Webb Space Telescope is out there, up and running, the real search for alien life can begin.